Chapter 16, solubility in complex ion equilibrium. When you think of, we're going to look at solubility first, and then the complex ions are one of the ways that you can increase the solubility of a slightly soluble compound. So we'll get to that second. First of all, what do we mean by solubility product? The reason it's called a solubility product, say we have a solid, and this concept of solubility can extend to any type of solvent. You know, it could be aqueous or non-aqueous, but for our purposes, we're going to stick with aqueous. So when we say solubility or equilibrium, solubility equilibrium, or solubility constant product, or whatever, we're talking about aqueous solutions. So if we're going to put this in the aqueous solution, then it's going to be, we're going to set up an equilibrium where this is going to be the cation and that's anion. These are in solution and that's not. In the first semester chemistry, we talked about, we got that chart where you could determine insoluble versus soluble compounds. And I hope I mentioned then that we were slightly soluble compounds, we were pigeonholing them into insolubles. Now we're going to pull them out and talk about slightly soluble compounds in aqueous solution. Silver chloride is one of those. So when we talk about solubility product, if we write the equilibrium expression for this one, then we would put the products, of course, here, and then we would want to put that one there, except that's a solid, right? So that goes out. That means that all is left, and for every solubility expression of equilibrium, we only have the product side, because these are always solids and they don't enter into the calculation. So that's why it's called solubility product, because it's the product of concentrations of the cation and anion in solution. Okay. And then, of course, if there are any coefficients here, then they go in as powers. Okay. So there's a difference between the solubility product and solubility. It's an intensity versus an extrinsic property problem. The intensive property would be the solubility product, because it doesn't change except with temperature. Whereas the solubility does change depending on the environment. So what do we mean by solubility? Well, we define solubility product. Solubility is how much of that goes into solution molar wise, the molarity goes into solution per liter of solvent. So if you have, if it's set up like this with only 1 and 1 and 1 here, then if you know the molar concentration of this one, so much molarity there, that's the solubility of the solid. And so many moles of this goes into so many liters. Now, if you have these coefficients, then in order to say anything about how much of this goes into solution, you need to take into account the coefficients. And we're going to work some of those in a minute. I just wanted to hammer that point home. Solubility product and solubility are two different concepts. It's like equilibrium when we were talking about equilibrium constant versus equilibrium position. So two different concepts. They're related, of course, but they're They're the same but different. No, not really the same. Okay. So the question becomes, if you calculate this KSP for a given temperature for a compound, does it always mean that, and you compare these for several salts, and remember what the chemical definition of a salt: an acid plus base equals a salt plus water. So we could derive these from HY and XOH reaction, and that would give us the XY here plus water. So that's why we refer to them as soluble salts, as slightly soluble salts, insoluble salts. But if we compare the KSPs for different, a list of different salts, does that necessarily mean that the one with the highest KSP will have the highest solubility? And the simple answer for that is no. And because, well, for two reasons. Because the simple expression of solubility is a molar concentration of the conversion of the solid into a into soluble ions. And the second reason is you've got those coefficients that go into the calculation here. If these have coefficients, then that can make this value very high. But if another salt has a KSP with only first power, then that would be very low. But they're so when you're comparing apples and oranges is the basic problem. So you can't say that KSP, the one with a higher KSP, has the higher solubility unless each of the salts has the same cation-anion ratio, right? If you have a list of them that are say this one's 2 to 3, and then you have another one that's like that. If you have the same ratios here, then the same calculations are going to give you a similar track for calculating the solubility. So in this case, if this is the case, if you have the same ratios for all of your salts, you can directly compare the KSP. Okay. But if they're different values, then you've got to do the grunt work. Okay. Now we're going to work some equilibrium problems, and S is a common value that we use for solubility. If we solve for S out of our ice table and we set it up right, then S should be the solubility. All right. So let's do one here. Let's use silver chloride. And the expression for the solubility of silver chloride, of course, is going to be an equilibrium of the solid with this cation and this anion. Okay. And the solubility product is this one says 1.6 times 10 to the minus 10. If you look in your lab, I think the one that the creators of that lab used was 1.7 times 10 to the minus 10, but it's still the same region. We'll use 1.6 because the slide's already made. Okay, what's the solubility here of silver chloride? Right, there's your equation. And that would be the expression for the KSP, would be the silver times chloride. And with single powers, So in this case, I don't know why we use X there. If we, let's set up an ice table just to be consistent. So initially, right, what do you have here? Well, you got 0, right? Before it goes into solution, you start off with nothing. And this doesn't count, so that's why I put the i's over here. Ice here, here, and here. So we're going to get some of that go into solution. And I'm going to use S here just to be consistent with future calculations. So we're going to add some of this, and we're going to add an equal amount of that. Well, if that's the solubility, then we know that over here we've lost that much. Right? But it doesn't have to be part of the table. It's just to verify that we put this into solution, and that is so many moles of this. If 1 mole of that goes into solution, it produces 1 mole of this and 1 mole of that. Okay. So that gives us S here and S here. So that means this expression would be S times S, right? So that'd be S squared, and that's equal to 1.6 times 10 to the minus 10. So we just take the square root of 1.6 times 10 to the minus 10, and we get the solubility of silver chloride in water at 1.3 times 10 to the minus 5. So S equals 1.3 times 10 to the minus 5. All right. What would it be? What would be what's the solubility of silver phosphate? Okay. Well, let's see. We might need this one, so I'm gonna put silver phosphate over here. It's going to be different. Why? Because phosphate has a 3 minus charge, and that's only 1 plus. So that means we need 3 of these, right? That's the solid. So we're going to set up an equilibrium with 3 silvers and 1 phosphate. And I didn't write the aqueous in there because I don't have room. So if we go to an ice table and set this up, I'm going to do this complete ice table for this first set, so you get the feel for it. Okay. So initial change and equilibrium. Initial, of course, is going to be 0 here and 0 here, and then the change. If we have 1 mole of that disappearing from this side, then what's going to show up on this side? We're actually going to add 3 on this side, aren't we? Yeah, because of the stoichiometry, and only 1 here. So now we have 3S and S. So if we set up our equilibrium here, we know that 1.8 times 10 to the minus 18 is equal to 3S to the 3rd power times S to the 1st power. Okay. So that would be 3 cubed is what? 3 cubed. That's 27. Yeah, that's pretty good. Considering your mental condition. And then 3 cubed and S, 1 cube, so it'd be S to the 4th, right? So all we have to do is divide this by 27 and take the 4th root of it. Let's see. Do I have it animate? No, I don't have it animate. But if you do all of that, you'll find out the solubility is 1.6 times 10 to the minus 5. Okay. Compare that to this one. It's a little more soluble. Slightly more soluble. But the KSP is way, way, way smaller. Okay. I think that's the whole point of that slide, is to see the disparity. Yeah. You can't just automatically say. Now, in this case, silver phosphate is more soluble. Well, no, that's a good point. It's more soluble, but it has a much, much smaller KSP. All right. So now we want to look at situations where we're not dissolving the solid in pure water, but we've got some other components in the water, you know, acids, maybe some common ions to the solubility here, right? Just for argument's sake, if we have some chloride already in solution, how's that going to affect the solubility? Yeah. Yeah, if you've already got chloride in solution, is it going to increase or decrease the solubility of silver chloride if you put some in the water? Think of the shot again. You've already got chloride there. It'll decrease the solubility, yes. Now, you don't have any silver there, so you will get some of it in solution. It'll move that way. But because you've already got some chloride in there, you're not going to get as much of it in solution as you would if it were pure water. Okay, let's take this example. How does solubility of silver chloride in water compare to that of silver chloride in acidic solution where the acid is nitric acid? Right. If it were hydrochloric acid, then we know it would decrease the solubility. But how about nitric acid? So how do we deal with this? Well, if nitric acid is part of the solution, right, that's going to be completely dissociated into hydrogen and nitrate ions. Right? So do they have an effect here? Well, silver nitrate is completely soluble, right? So it's not going to affect this side. And HCl is completely soluble. If you think of it in those terms, where this dissociates, what's that going to try to associate with? Well, it's going to try that one, right? But it's completely soluble. And this one associated with that anion, that's completely soluble too. So nitric acid in solution has no effect on the solubility. There's no common ions there, nothing to interact with that would alter the equilibrium here. Okay. And this is another way to look at it. Add those two together, right? And you get something like that. And what we're actually saying is that hydrogen and nitrate are spectators. They really don't enter into the reaction at all. Okay. How about silver phosphate? Okay, let's move over to this side. How would adding nitric acid affect this one? If we have the HNO3 is going to completely dissociate into that one plus this one. Right. So which one would nitrate interact with? Well, silver again, right? Anion, cation. Right? It's completely soluble. But phosphate and hydrogen, how are they going to interact? Remember, we put phosphate in solution, right? We did a calculation in the one of the previous chapters, 14 or 15, with the concentration of phosphate in equilibrium. If we put phosphoric acid in solution, it would dissociate one hydrogen at a time until we get down to phosphate. And it was like 10 to the minus 19th. But there's still some there. And since there's only a small amount, and because it's the last one in the string, that phosphate is going to be an extremely strong base. It's going to go hunting for hydrogens. Because we know the equilibrium at that point produces very little of it. It prefers HPO4 2-. And then once you get to that point, that's a pretty strong base too, and it picks up another hydrogen and then another hydrogen before it gets to phosphoric acid. So what's going to happen is these two are going to combine and produce HPO4 2-. Okay. So what does that do to this equilibrium? Well, it removes that product from the equilibrium. Right? It's not part of that equilibrium anymore. It's down here with a different one. So if we remove something from this side, Le Chatelier says, going that way, it's going to make the silver phosphate more soluble by adding an acid. And that's true for any solid in aqueous solution if the anion of that salt is a strong base, then all you have to do is add some acid and it will increase the solubility. Okay, that's one way to increase solubility, is if the solid will dissociate into a cation plus a strong base, then adding an acid will always increase its solubility. Okay, and there's the explanation. Let's see. What did we do between those two? Okay. Yeah, we reacted the hydrogen with the phosphate and made HPO42 minus. And that drove the reaction to the right. So that's one way to get a slightly soluble salt into solution, increase its solubility. If, on the other hand, you have something like this, and it dissociates into this one and that one, chloride is not a strong base, right? Whereas it's derived from HCl. Right? So it's a very weak base. A strong acid makes a weak base, so it doesn't want hydrogen. So it doesn't matter if you put nitric acid, if you put hydrogen ions of any kind in there, then it's not going to increase the solubility. Now, of course, if you put something else over here, like we did with the chloride, that's going to decrease the solubility. So we need another way to approach this problem and get that salt into solution. And since we can't tackle that one, we tackle this one. And that's where complex ions come in. If we can take this out of that equilibrium by making a complex ion out of it, then we can increase the solubility. So those are the two ways that you can increase solubility of a salt, depending on its nature. If the anion is a strong base, just acidify it. If the anion is a weak base, then you find a complex ion for the cation. And there are a whole host of them there on that page. That's not exhaustive by any means, but those are the most common ones. Okay, how's the KSP of silver phosphate in water compared to that of silver phosphate in acidic solutions made by adding nitric acid, for instance? How does the KSP compare in those two situations, water or nitric acid? It's kind of a trick question. The KSP is a brain farts. The KSP is a constant. As long as you don't change the temperature, the KSP is constant no matter what you do to the solution. Right? So we talked about solubility here with adding common ions, but that doesn't change the KSP at all. So when we do calculations, say we have a solution where we've got a slightly acidic, right? Then we need to set up our ice table to take that into account. Or where we have, well, something else. If we put chlorides in solution, then the initial concentration goes in here. And then we have to take that into account with our calculations. And we can actually calculate what is the solubility if the chloride concentration is a given amount. Right? So the KSP doesn't change as long as the temperature is constant. It's kind of like that statement where no matter what acid-base reaction you're talking about in solution, KW is always there. It always happens. All right. So let's see, what are we going to do here? What's the solubility of silver chloride in 100 milliliters of 4 times 10 to the minus third molar calcium chloride? Okay, chloride's a common ion, so we can say qualitatively, we're going to decrease the solubility. And the solubility in pure water is right here. Right? That's why I left that up there. So we can compare it to the next calculation. Right? And what's this? Okay. We still have an expression for solubility as S. And so some of this is going to go, but we've changed this value, right? That value is now 4 times 10 to the minus 3. Okay. So now we're still going to move to the right because that was 0. And so we're going to add an S over here. And that means that for every one of these, there's one of those. So that means we have another S over here. But at equilibrium, we're going to have an S here, plus we're going to have a 4 times 10 to the minus 3 plus S. Okay. So now if we set up the problem here, I better do it over here. So the KSP is equal to 1.6 times 10 to the minus 10. And that's equal to this value times this value, 4 times 10 to the minus 3 plus false. Let me see if this is worked out. Yeah, there's our table. Excuse me, why did I say 2? Oh. Duh. What did we put in solution? 2 chlorides. 2 chlorides for every one. There we go. So this is going to be 8. Okay. So there's our expression that we have to solve. What we're saying is that the solubility we know in pure water is 10 to the minus 5. We know that the solubility is going to be even less, right? Qualitatively. So with that such a small value, then S is going to be even smaller relative to this value, and we're going to drop that S from here, just so we don't have to solve a quadratic. So that's approximately, well, if we drop that S, that means 8 times 10 to the minus 3 S is equal to that. So we just say we divide that value into this value, and that gives us S equals 2 times 10 to the minus 8 molar. So it's 3 orders of magnitude less soluble. Now, I didn't do 5% on this one, did I? Since we got time, let's run the 5% just to be sure. All right, so if this is the solubility, then we need to put this value in here and here and see if it's equal to that. So if we do that, that means our KSP calculated would be equal to 2 times 10 to the minus 8 times 8.8 times 10 to the minus 3 plus 2 times 10 to the minus 8. Okay. So let's see what that is. and 8 multiplied. 1.6 times 10 to the minus 10. Exactly. The reason for that is this is 5 orders of magnitude smaller than that. So it doesn't change it whether it's this way or that way. Okay. I'm happy. Okay, so we know the we can calculate the concentration when there's a common ion effect involved. I didn't even focus on the 100 milliliters because in this case, 100 milliliters doesn't matter. If we know the concentrations already, it could be 10 milliliters, could be 100 liters. Now, of course, if we have 100 liters, the solubility in molar terms is going to be the same. But 100 liters versus 100 milliliters is going to dissolve a lot more, right? So extrinsically, capacity factor, we're going to get more of that in solution if we have more volume. Okay, how about calcium nitrate? If we have that calcium nitrate instead of calcium chloride, well, nitrate is, we've already decided it's not going to affect that. And where does calcium fit in? Well, calcium chloride is soluble too, right? We did one with calcium chloride. So calcium nitrate is not going to affect the equilibrium at all. So that just means we're back to pure water. Okay. Now, suppose we do have a solution that has a known concentration of anions and known concentration of cations. Then what we want to do is try to predict. We're starting from the other side now. Instead of starting from the solid and trying to get into solution, we're starting with a solution of, say, a mixture of cations and anions. And we say, are the concentrations of those in there high enough to give us a solid? Right, we're working the other direction now. Instead of going this way, we're going that way. And to do that, we compare the Qs. Right? We can calculate a Q product if we know the concentration of silver and chloride ions in solution, for instance, and compare that to the KSP. Well, if the Q is big enough, right, if this is high enough and it exceeds the KSP, we're going to get some precipitation, right? Some of it will still be in solution, but we will get some precipitation. Right? Whereas if the Q is less than the KSP, we will get no precipitation. Okay, and that concept is used to selectively precipitate, usually metal ions, from solution by adding certain cations and changing the pH of the solution. We can do successive precipitations and separate a complex mixture of cations, metals, as a first step. Usually, if it's very complex, then you're going to get just a separate solution with 3 or 4 out of that mixture, and then 3 or 4 the next one, 3 or 4, and then you have to go through and work out how to get those others apart. But for our purposes, we're only going to look at selective precipitations as a sort of a flow chart of how to get ions separated, metal ions separated out of solution. Right. So this comes under the topic of wet chemistry or bench chemistry. Now, all you want to know is the concentration of the various metals in solution. We can do that. All we need is, I don't know, $300,000 or $400,000. set up your inductively coupled argon plasma spectrometer, and you can analyze a solution and find out what the concentration of each one of them is. As long as you don't need to separate them from one another, right? It's a destructive process. But I used to do that on a regular basis. Now, the first instrument I was had access to at, let's see, where are we? Over there, was about $1.5 million. And by the time I replaced that one with a newer generation, the price had come down to like $300,000 or $400,000. Still crazy. But it was a service lab. I was running a service lab for 15 research scientists, so they could justify paying my salary and buying the equipment, because they would have various things, like the plant materials, they have soil samples, they have other types of solutions that were gathered from experiments, and they wanted to know, right, what's the metal concentration, elemental analysis for research products. And depending on what they were, if they were already in solution, all I had to do was make sure that they prepared them correctly so we wouldn't lose anything in the process. If they were plant samples, I'd have to digest them, right, put them in solution. Or if they were soil samples, I'd either have to digest the soil samples or extract them however they wanted it, and give them a report.
Was that here?
Yeah, that was over across from the Mine Academy at the Agricultural Research Service lab. Yeah. So I'm sure they spirited that equipment away before we got to it, because we used to own the building. It was donated to us, and we decided our budget couldn't handle maintenance on it, so we gave it back to them. But in the meantime, I made a couple of trips over there, and I scoured the place for stuff and stocked up our lab with things, glassware, a few chemicals. There weren't many chemicals left, but I made sure there wasn't anything left that was valuable, except I sure wish we could have gotten the centrifuges. No, we didn't have any place to put them. Yeah. If we had, huh?
How expensive are those?
We had one regular, just refrigerated centrifuge that has the spin heads were about that big around, and you had different size tubes you could put in them, and the atmosphere inside was just air, and so you could spin those up to 10 or 15,000 RPM, something like that. And then we had another one that was evacuated. You put it, set up your, and balance it. You have to be real careful to balance it correctly. Put your head in, slide the door closed, and lock it, and then evacuate the chamber, because it was going to spin up in the tens of thousands of RPM. I was a support scientist, and the research scientist I was working under was biochemist. So they like to do that stuff, spin stuff down. That was one of the things we did. And I wish I could have got hold. Oh, you asked me how much they were. The cheaper one was probably in the neighborhood of 20,000, 15 or 20,000. The ultra centrifuge was probably 100,000.
Price of the car and house.
But the thing about those also is they need regular maintenance by a pro.
Yeah.
So it probably would have cost us too much to keep them up anyway. And then I had one that was it was a soil centrifuge. It was just a big, it sat on the floor, and it had it was a bucket centrifuge. It had different heads for it, but they had swinging buckets on it, and you could put, I mean, you could just eyeball it for a balance. It was that sturdy, and you just spun it up. It maybe 3,000 RPM at most. Right. Then we had the little bench tops centrifuges like you see in medical labs with tiny tubes.
Yeah,
and those two. See, I get to digress.
Yeah.
Okay, but before we had the ability to analyze these things with argon plasmas or even atomic absorption spectrometers, where you shine a light through it and you measure the intensity on one side and the intensity on the other side and ratio them, and that was proportional to the amount of that element that was in the solution. And that was usually, you'd suck them up into a acetylene flame. And if we really needed to get hot, we could introduce nitrous oxide in there, and the flame would go from that high to like that. It's like drag racers. But anyway, before we had those instruments, and by the way, the atomic absorption spectrophotometer was invented in Australia, in case you're interested. So what we want to do, if we've got a mixture of cations or metal ions that we want to separate, then we've got to pick our anions correctly and the environment, right? Whether it's acid or basic or neutral makes a difference also. Pick the environment so that we can selectively separate the ions as precipitates. So in this example, we've got barium and silver ions that we want to separate. We know that if we add hydrochloric acid, the chloride is going to combine with the silver and drop out. Question is, does barium chloride, is it soluble? The answer is yes. Barium chlorides are soluble. In fact, most chlorides are soluble for the metal ions. There are only a few chlorides that are insoluble. Silver is one of them. Let's see. Silver, I think mercury is insoluble. It escapes me. The others that are insoluble. Anyway, we know we need to get that common ion, that chloride, in there to make silver precipitate. And the choice of chloride ion is important, because if you put just any chloride compound in there, you'll get the precipitate, but you'll also contaminate the solution. So if we did it with sodium chloride, we'd get the silver out, but we'd have sodium and barium together, and we wouldn't have access to barium then, except maybe with some very tedious other wet chemistry. So hydrochloric acid is probably the best choice to separate those two ions. So in this example, we're going to separate copper 2 plus, mercury 2 plus from nickel manganese, nickel 2 plus and manganese 2 plus, using hydrogen sulfide. So what do you think we're going to form from this if we get them separated? Well, the sulfide, like the sulfide of the metal. So what we find is at a low pH, the sulfide ion is relatively low. And only the very insoluble mercury 2 sulfide and copper 2 sulfide will precipitate. So the first reaction we want to do is hydrogen sulfide, right? And this is aqueous. So we've got another equilibrium set up here with these two products. Okay. Well, this equilibrium in pure water is predominantly over here. Hydrogen sulfide, it's aqueous, it's in solution, but it doesn't produce these ions, and we need some of that ion, but we don't need too much of it. Right? We just need a little bit of it. So the way we do that is we acidify the solution. We make sure that we've got plenty of hydrogen ions in there. So if we add hydrogen ions to this solution, say with nitric acid would probably be best. Then that's going to drive this reaction to the left, right? And produce very small amounts of sulfide ions. And that will take out the least soluble compounds of mercury 2 and copper 2 sulfides. Okay. Oh, there's the evidence. All right. So what I did where I combined the two equations, this is an acid, right? Hydrosulfuric acid, and it dissociates one hydrogen at a time. The HS minus will not react with those cations. So we need sulfide. So that's why we went through both steps and then we combined the two to find what the overall is. The overall in water is 10 to the minus 20. But we're going to add more of this and decrease it even further. Well, we're not going to actually, I misspoke. We're not going to change the K at all. We're going to change the equilibrium position by adding hydrogen ions. The K is the same no matter what we do to it. So after we get the copper and mercury out of solution, then we can increase the concentration of sulfide and precipitate the others, right? So in order to do that, now we add a base. It combines with this, makes water, right? We know that 10 to the minus 14th is the equilibrium constant for water, which means it's mostly water, right? It's going to water and have very little of this. So when you add hydroxyls there, it's going to pick up those hydrogens, make water, and drive the reaction this way and produce a lot more of that. Okay. Now that we've got more of this, then we can precipitate out the others, the manganese and the nickel. Now, when we precipitate copper and mercury, you don't want to leave them in there, do you? Right? When you do the next step, how do you get them out? That's not a trick question. Filter them. Right? Just run them through a filter. If the pore size is small enough, then you can catch the precipitate in your filter. And then the filtrate that comes through has very little of the copper and mercury left. It might have some, but hopefully it'll be just minuscule amounts. And then you can precipitate out the rest of it, and that's your nickel and manganese. Okay. And we've got systems that'll filter out, I mean, on the nanometer scale.
Is that what we're going to do in the lab?
No, no, we're not going to do a sequential precipitation. I mean, that'd be a good lab. Yeah. What we're going to do is solubilize silver with ammonia. And then we're also going to calculate, we're going to titrate that solution with potassium chloride and run through calculations that tell us what the solubility, the formation constant for the complex ion is. I'll get to that as soon as when we talk about the intro to the lab. Now, that would be a good one. Let's see. Where was I? Okay, so we filter them. For this is the flow chart for that. And if we have an acidic hydrosulfuric acid, then we can precipitate the copper and the mercury. And then if we add a base after that, we can get the manganese and the nickel. And filter between steps. Okay. So if we use that concept and we have a mixture that's This came straight out of your book, so it's kind of small here. But we've got a mixture of all these, and notice they're color coded. So the first step for this, it's color coded in groups. So this is group 1, this is group 2, group 3, group 4, and group 5. So silver, lead, and mercury 2+. If they're in that solution, then we add hydrochloric acid. Hydrochloric acid will take out the silver, the lead, and the mercury. Okay, filter those out, take that solution. Now, since it's already acidified and we've used up the chloride in precipitating the first group, we don't have to worry about the chloride anymore because we filtered it out as the solids. Then we can, and it's already acidified, now we add hydrogen sulfide to it, the hydrosulfuric acid. And that'll take out the very slightly soluble, the least soluble sulfide compounds in group 2. And group 2 is composed of copper 2, bismuth, cadmium, lead, mercury, arsenic, antimony, and tin. So there you still have a fairly complex mixture. So this is only a first step. After you get those out and filter those out, then you can take that solution and add a base to it. And now you get the sulfides that are more soluble, because now you got more sulfide in solution. It's going to drop those out of solution. What we've done is, by increasing that sulfide, we've boosted the Q past their solubility products. Now they're going to drop out of solution. That's group 3. Group 4, now we're going to take those out with sodium carbonate. Okay, sodium carbonate, remember, if you put sodium carbonate in solution, we talked about that last chapter, right? Strong base, weak acid, right? It's going to be a basic solution. Solution's already basic, so this is going to make it more basic, only add carbonates. And the rest, the group 4 is going to drop out as the carbonates. They're going to be barium, calcium, and magnesium carbonates are going to drop out, and we filter those out. And then the 5th group is what's left, right? The alkali metal ions and ammonia. They're all that's left now. We're not going to delve into what you do with these complex mixtures afterwards. It's too complex for this class. But that's a selective precipitation procedure. So I'm not going to have you memorize these groups and which ones take out which, but you need to be familiar with that chart so that if you're given that chart, you can interpret it and know what to do with it. Okay, I'll say that much. Okay. Now we've talked about acidifying a solution where the anion of the salt is a strong base. That will increase its solubility. But where the anion is a weak base, like silver chloride, we have to attack the cation side to get into the solution. And that's what we're going to do with complex ions. Some terminology, right? We have a metal ion that is charged, right? In this case, silver. And we're going to surround it with what we call ligands. Ligands is from the Latin for leg, I think. So it has various legs, and it depends on the metal and the ligand as to how many associate with it. In this case, silver only associates with 2 ammonias, right? So if we have 2 ammonia, and it has to be NH3. Ammonium will not complex. It has to be NH3. And what do we know about this one? It has those 2 lone pairs. Right. So an electron pair acceptor is a Lewis acid, correct? An electron pair donor is a Lewis base. So this is the base donating electrons to the silver. And when it does, it forms a covalent bond. and in an equilibrium with this silver ion and two ammonias. And it still has that one charge here. This is uncharged, that's charged. So it still has that charge, and this is soluble. Okay. So when we remember when we were looking at Le Chatelier's principle with our last lab, and I hammered this point home. If you want to affect a change in the equilibrium, sometimes you have to couple it with another reaction, which is what we did many times. So what we're doing here is coupling this reaction with this reaction. Right? So if we form this complex ion, it shifts the equilibrium that way and removes this one. So if we're removing this one from solution, these are both in the same solution. If we're removing that ion from solution to form this ion, then it's also removing it from this side and increases the solubility. And if you get enough of it in there, you can completely dissolve silver chloride, get it in solution. Right? And that's what we're going to do when we set up our solution before we titrate it. We're going to add enough ammonia that we get all of that silver chloride in solution. Actually, the way the experiment is set up, silver's in there as silver nitrate. Right? So it's already in solution. We're just going to take all of it and make that with it. You know, almost all of it. There'll be a little bit of this left over. And in fact, there's this equilibrium is set up so there's a little bit of that left over. And as we add chloride ion with potassium chloride during the titration process, we're going to strip this away from here and start shifting that back here. But there's a competition here, right? This keeps wanting to do that. So we're looking for the balance point. When we're adding chloride ion, we're looking for the balance point where it's just at the point where you start to form that. That would be the equivalence point or the end point of this reaction. When you see that formed and it stays. Okay. So the KSP for this would be written how? Actually, it's not KSP. It's KF. Formation constant. Because we're not solubilizing anything, it's already soluble. So the formation constant would then be product divided by reactants. This one is 2. So that would be the expression for this equilibrium. And that's a constant. That's what we're getting at with the lab. Here's another example. So this idea, formation constant, the creation, is like an acid dissociation, right? One proton at a time. Each one, as we add a ligand, has its own equilibrium. So this is an overall expression. But in fact, you're producing silver plus 1 ammonia to make silver ammonia plus, and then you're taking that one and adding another ammonia. So you actually have a K1 and a K2. In this case, we've got beryllium and fluoride. And this one has 4 ligands. Fluoride is the ligand in this case. So we've got a K expression for the first ligand, for the second ligand, for the third ligand, for the fourth ligand. And notice they're all greater than 10. All right, the last one is 27. The next to the last one is 610. The second one in the series is 5,800. And the first one is 79,000. right? So the first one is the highest K value shifting to the right, but they're all shifted to the right substantially. So overall, the K value for the overall formation of this complex ion is 10 to the 12th. Now let's see. If I were going to name this, I would call it, let's see. This is a negative. It's a negative ion, so we named it a little different. So this would be tetrafluoro beryllium 2 ion. Yeah. Okay. So this slide just hammers home the concept. How do you get slightly soluble compounds in solution? Two strategies. One is if the anion of the solid is a good base, it's a strong base, then all you have to do is acidify the solution. If not, then you have to attack the cation forming complex ion. Oh, we got Saul Kahn's going to talk to us now.
First, let's calculate the molar solubility of silver chloride in pure water, and then we're going to compare the solubility that we get in part A to the solubility that we're going to get in part B. And in part B, it's no longer pure water. We're going to have some ammonia present. So we take some solid silver chloride, so that's this over here, and we put it in some pure water, and some of the silver chloride is going to dissolve, but most of it's going to stay in the solid form. So silver chloride is only a slightly soluble compound. So there's my little pile of undissolved silver chloride. But some of it does dissolve, and so we get a saturated solution of silver chloride. So there are silver +1 cations in solution, and there are also chloride anions in solution, and we have our solubility equilibrium. To find the molar solubility of silver chloride, let's go ahead and write down our ice table. So our initial concentrations, our change, and finally our equilibrium concentrations. Before we put the silver chloride in, we didn't have any ions in solution. So the initial concentrations of our product are 0, right? We have 0 for the concentration of our ions. Some of the silver chloride that we put in dissolved. So we lost a certain concentration of our silver chloride, and we're going to call that X. So we're losing a certain concentration of our silver chloride. If we look at our mole ratios, for every 1 mole of silver chloride that dissolves, we get 1 mole of silver +1 cations in solution. So if we're losing X over here, we're gaining X. We're gaining X for the concentration of silver cations in solution. And since our mole ratios are still 1 to 1, if we dissolve 1 mole of silver chloride, we gain 1 mole of chloride anions. So over here we get a +X. So at equilibrium, our concentration of silver cations is X, and our concentration of chloride anions is X. So we write our equilibrium expression, and since this is a solubility equilibrium, we're going to write KSP, our solubility product constant, is equal to concentration of our product, so that's concentration of Ag plus raised to the power of the coefficient, so raised to the first power, times the concentration of chloride anions, Cl minus, raised to the power of the coefficient to the first power. So we can plug in our solubility product constant at 25 degrees. It's 1.8 times 10 to the -10. So we put in here 1.8 times 10 to the -10. And this is equal to, this would be X times X. So this is equal to X squared. So we can get out the calculator and solve for X. So we have the square root of 1.8 times 10 to the -10. So we take the square root of that, and X is equal to 1.3 times 10 to the -5 if we round that. So X is equal to 1.3 times 10 to the -5 molar. So that's the concentration of, let's say, our silver +1 cations in solution. That's also the molar solubility of silver chloride, right? That's how much we can dissolve. So it's a very small molar solubility. So silver chloride is only a slightly soluble compound. Let's see what happens when we have ammonia present instead of pure water. So we have a 3 molar, right? We have some ammonia present now. What happens when ammonia is around silver cations? All right, we get this reaction. So silver cations plus 2 molecules of ammonia give us what's called a complex ion over here. And let's show what's happening. So if we have a silver +1 cation, right, we have 2 molecules of ammonia. So let me go ahead and draw in my 2 molecules of ammonia. And this is certainly not drawn to scale. So I'll draw one in on that side. I'll draw another one in on this side. Remember your definitions for Lewis acid, Lewis base, right? A Lewis base is an electron pair donor. And that's what's going to happen here. The nitrogen has a lone pair of electrons, and each ammonia molecule is going to donate a pair of electrons to our silver +1 cation. Right, so ammonia is donating as an electron pair donor, so this must be our Lewis base. And the silver +1 cation is accepting a pair of electrons, so this must be our Lewis acid. So the formation of a complex ion is a Lewis acid-base reaction. And notice the equilibrium constant for this, 1.6 times 10 to the 7th. Kf is called the formation constant. This is a very high value for the equilibrium constant, right? So the equilibrium lies to the right, and this is a stable complex ion. So any silver ions that are in solution, if you have ammonia present, ammonia is going to pick up that silver ion and essentially remove the silver ions from solution. So if we go back up here and think about our equilibrium, right, if we have ammonia present, we're going to be removing silver cations from solution. Right, so we're decreasing the concentration of silver cations. We're decreasing the concentration of one of our products. And Le Chatelier's principle says if we're decreasing the concentration of one of our products, our equilibrium is going to shift to the right to make more. Therefore, increasing the solubility of silver chloride. More is going to dissolve because the ammonia is present, because of the formation of our complex ion. So if we added some ammonia, right, if we added a solution of ammonia here, we could get our silver chloride to dissolve, right, because it's more soluble because of the formation of a complex ion. So let's say we add enough ammonia solution where we get our silver chloride to dissolve here. So that's the idea. Adding our ammonia, right, caused formation of a complex ion, which increased the solubility of our silver chloride. So we would expect an increased solubility here of our slightly soluble ionic compound, silver chloride. And next, we're going to do the calculation. We're going to find the solubility of silver chloride in our 3 molar ammonia solution. Now we've looked at 2 reactions. We've looked at the solubility equilibrium for our slightly soluble compound, and we've also looked at the formation of our complex ion. Now let's add those 2 reactions together to get our net reaction for what's happening, right? So we're going to add our 2 reactions together to get a net reaction for what happens when you put silver chloride in ammonia. Right, we have silver cations on our reactant side and on our product side, so we can take those out. And so for our reactants, for our net reaction, we have solid silver chloride plus ammonia. And for our product side, we would have our complex ion and our chloride anion. So we have our complex ion, and we also have chloride anions, so Cl-. So that's the net reaction, and if we added those 2 reactions together to get our net reaction, we have a new equilibrium constant, which I will call K. And if you add 2 reactions together to get your new equilibrium constant, you multiply the equilibrium constants of those 2 reactions. So K is equal to KSP times KF. So if you did that calculation, 1.8 times 10 to the negative 10 times 1.6 times 10 to the 7th, you'll get your new equilibrium constant. And I won't do it here just to save some time, but if you do that, you'll get 2.9 times 10 to the negative 3rd. So that's a 9, 2.9. All right, our goal is to find the molar solubility of silver chloride in our ammonia. So we set up our ice table, so our initial concentrations, our change, and then our equilibrium concentrations. And let's pretend like we're starting out with our solution of ammonia and we haven't added any silver chloride yet. So let's go back up here and let's see what our concentration was. Well, we started with a 3 molar solution of ammonia, so let me put that down here. So our initial concentration for ammonia is 3 molar. And if we haven't added any of our silver chloride, then we don't have any of our complex ions. So the concentration, the initial concentration of our complex ion is 0, and we also wouldn't have any of our chloride anion either, so that concentration would be 0 too. So now we add our silver chloride to our solution of ammonia, and some of our silver chloride is going to dissolve, and so we make that concentration X. So we're losing a certain concentration of silver chloride, so we write minus X. Next, we look at our mole ratios. So the mole ratio of solid silver chloride to ammonia is 1 to 2. So for every 1 mole of silver chloride that dissolves, right, we're also going to lose 2 moles of ammonia. So we write minus 2x here. For our products, if 1 mole of silver chloride dissolves, we make 1 mole of our complex ion. Right? So if we're losing X over here, we'd be gaining X over here for the concentration of our complex ion. And same thing for the chloride anion, because our coefficient is a 1. So we're going to gain X for the concentration of chloride anion. So at equilibrium, our concentration of ammonia is 3 minus 2x, our concentration of complex ion is X, and our concentration of chloride anion is also X. Next, we write our equilibrium expression. So K is equal to concentration of products over reactants. So I look at my complex ion over here, so concentration of our complex ion, and we raise the concentration to the power of the coefficient, so to the first power. This is times the concentration of our chloride anion, so times the concentration of chloride anion raised to the power of the coefficient, so raised to the first power. We also have some reactants here, so we leave silver chloride out because that's a solid, right? But we have ammonia, so this is all over the concentration of our reactant, so this is over the concentration of ammonia. And notice our coefficient is a 2, so we need to have a 2 here. Next, we plug in our equilibrium concentrations. So our equilibrium concentration of ammonia is 3 minus 2x, our equilibrium concentration of complex ion is X, and our equilibrium concentration of chloride anion is X. So on the right side, we would have X to the first power times X to the, let me take that out, times X to the first power. Right, all over 3 minus 2x to the second power, so squared. And then we can plug in our equilibrium constant k, which is 2.9 times 10 to the negative 3rd. So 2.9 times 10 to the negative 3 is equal to, on the right side, we would have x squared. So let me write this out. We would have x squared over 3 minus 2x squared is equal to 2.9 times 10 to the negative 3rd. And so what we could do here, these are both x squared, right? These are both x squared, so we could just say that this is all squared on the right side. And then we could take the square root of both sides, right? So take the square root of 2.9 times 10 to the negative 3rd, and take the square root of what's on the right. So the square root of what's on the right would be x over 3 minus 2x. And let's take out the calculator to do the other one. So square root of 2.9 times 10 to the negative 3rd is equal to, let's round that to 0.054. So it just makes it easier here to round that. So 0.054. Our goal is to solve for x. Our goal is to solve for the molar solubility. So we can multiply both sides by 3 minus 2x. So when we do that, right, we would have this. So we need to multiply 0.054 by 3, and if you round that, you're going to get about 0.16, and 0.054 times 2 is approximately 0.11. So we have 0.16 minus 0.11x is equal to x. So we have 0.16 is equal to, we put both x's on one side. This is 1x, and this is 0.11x. So 1x plus 0.11x is 1.11x. And so now we need to solve for x. Right? So we've done our math here. So we have 0.16. We need to divide that by 1.11, and that is equal to 0.14. So x is equal to 0.14, which is only approximate because of all the rounding that we've done. So this is concentration, right? So this is our molar solubility. If we go back up here, x equal to 0.14 molar, right? So that's our concentration of complex ion in solution at equilibrium. That's our molar solubility of silver chloride, right? So it's 0.14 molar. Let's go way back up to the beginning and compare the molar solubilities. Right, so in pure water, the molar solubility of silver chloride is 1.3 times 10 to the negative 5 molar, which isn't very soluble at all. But now we have ammonia present. We've increased the solubility, and we just calculated the molar solubility is 0.14 molar. And obviously 0.14 molar is a lot larger than 1.3 times 10 to the negative 5. So the formation of a complex ion increased the solubility of our slightly soluble compound, silver chloride.
So we've done this combination. And there's our two reactions. This one is 1.6 times 10 to the minus 10. This is the formation reaction for the complex ion. Well, actually, that's the first one. And here's the second one, where we take the first ligand side and we add another ammonia to it. That gives us the K2. So what would be the all right, we're saying that the complex ion formation is way, way, way far to the right. Yeah. So let's see. If we combine those two reactions to get this one, what would the K be for this one? Right. It would be K1 times K2, wouldn't it? So what's K1 times K2? I have to use my calculator. 2.1 exponent 3 and 8.2 exponent 3 times 1.7 times 10 to the 7th. So it is way, way far to the right. We multiply those two together. But in solution, we've got both of these things going on. So if we combine all three of those reactions, what are we going to get? Let's see. We're going to have silver chloride solid on this side. We're going to have silver ions, and we're going to have ammonia here. That's aqueous. All right. And then we've got silver on this side and chloride and the complex ion. Aqueous. Okay. Let's see if I got a slide. Yeah, there we go. So what we've done here is get rid of the spectators. Get rid of this one because it's on the same on both sides. So that's the reality, that expression right there. And what would its K be? If we write the K for this expression, we get 2.75 times 10 to the minus 3. So the K for this combined equation is 2.75 times 10 to the minus 3. Right. Well, what was it? What was it with just the silver chloride and water? Let's see. Was it 10 to the minus 7? I think it was, wasn't it? Silver chloride and water. No. 10 to the minus 10.
Yeah, 1.6.
10 to the minus 10 for silver chloride and water. KSP is 10 to the minus 10. So we've increased the K value for this reaction by 7 orders of magnitude. And if we actually want to get all of the silver in solution, we need a very high ammonia concentration. All right, so let's do a calculation. I thought we were going to use S's, and we keep using X's. I like to use S's. If X is the solubility of silver chloride, the following ice table tracks the changes that produce equilibrium. So there we have this equation. And if we set up our ice table with ammonia, that one's not in there, right? Because it's a solid. It's not in the expression here either. Then we have ammonia, we have chloride, we have the complex ion. So if we're looking at this in terms of, okay, we didn't give it all the information here. We're starting off with 10 molar ammonia. Right. So we set up our ice table. And we're saying we're going to use 10 molar ammonia. That's pretty high. With 0 here and 0 here. And then if we're going to put X of this in solution, right? Well, let's use S. I'm going to use S. We're going to put that much in solution. And what does it do down here? Well, we know that for every one of these, we should get one of these, right? And for every one of these, we should get one of those. So this is going to be plus S. But for every one of these that forms, we have to use up 2 ammonias. So we're going to subtract. Keep my own convention. There we go. We're going to use up 2 of those. So that means we have 10 minus 2S here. We have S here. Right? So there's our expression. We get these 2 values. Wait a minute. Oh, this is the formation constant. This is not the K for this expression. The K for that expression. So I guess I can put it down here. The KEQ for that expression would be the complex ion and the chloride there. And then down here, we have the ammonia squared. So we plug those values in, and then we have to decide, are we going to need to call X insignificant? Well, fortunately, what we've got here, let me go ahead and write it out. What we've got here is these 2 S's are going to be S squared, right? And this one's going to be 10 minus 2s squared. Right? So if this one's squared and that one's squared, it's the same thing as writing s over 10 minus 2s, and the whole thing is squared, correct? So we don't have to make the assumption that 2s is going to be small, because all we have to do now is square both sides. Right? Square root both sides. Square root of this would be that expression and that expression divided by that expression, and then the square root of the k. So I think that's what we do next. Here we go. So we take the square root of both sides, and that's what we get. And then if we solve for x, get it on the next slide. There we go. Then if we solve for s in my case, there we go. There we go. And now we don't have any squared s's. We just have to solve for the s, 0.47 molar. So what does that mean? That means we've, the solubility of silver, since it's related 1 to 1, and this is s, right? This is s. So we're saying that we put 0.47 molar concentration of silver chloride in solution as a consequence of this reaction. Whereas the solubility before was, what was it? In water, that's KSP. Solubility was 10 to the minus 5, 1.3 times 10 to the minus 5. So S before was 1.3 times 10 to the minus 5 molar versus 0.43 molar. So we've increased the solubility by over 4 orders of magnitude by adding ammonia. Let's see, what am I doing over here? Oh, what's left over, right? If we wanted to know what's left over of the ammonia in solution, there's a lot of it left, right? 10 minus 2s. If we solve for this part right here, that tells us what's left in it at equilibrium. 9 molar. So we have to have a lot of ammonia in there to accomplish this solubility. Oh, that's it. Okay. And we're 25 minutes away from lab time.
So Tuesday, we're gonna do a review for this.
Yep.
And
Tuesday is a holiday, isn't it?
I think it is July 4th.
Yeah, July 4th.
Okay, so
We'll do a review on Thursday and have a lab on that day.
gotcha. And then the next Tuesday will be test.
Yeah. Yes. Then we'll be back on schedule.
Gotcha.
Well, normal schedule.